Hi everyone, welcome to this course, Introduction to Statistical Mechanics in Soft and Active Metal Systems. So, we were discussing about the generalized form of fluctuation dissipations, and for that we first tried to calculate the time autocorrelation in random in generalized random forces, right? So we were discussing that how this general fluctuation distributions theorem look like, and in the previous class we sort of discussed about few things regarding the generalized Langevin equations for the particle configuration systems, and we also tried to see that how these reciprocal relations can be proved by using Onsanger's time way, where he used the time reversal symmetry, to prove that the reciprocity of these coefficients. Although the Onsanger tried, or Onsanger proved the whole reciprocity relations using irreversible thermodynamics, but here we used the system in our hand, which is Brownian particle system, Brownian dynamics, and we tried to calculate that. Okay, so that's that. Then we will restart our discussions so that we can get the time correlations of the random forces. Okay, so if that's the case, let me share my screen. I hope you guys can see my screen here. Yes. So let's start our discussions where we have left from. Okay, so we calculated the we have written the equations, or the Lagrange equations for this system, right? So we have written the microscopic equation for this Brownian particle from the Hamiltonian's principle, and then we try to calculate the uh, macroscopic force functions from this microscopic instantaneous force, right? So where we have used this microscopic force, and we since this is the Fi, the microscopic force, so from that we can calculate the macroscopic force using this relevant distribution function for of this force, and taking the average like this. Okay, that we will do here also. Okay. Okay, so now we can write our relations like this. huh? Now in the fluid, since if the fluid molecules are at equilibrium, for a given value of x, which is x is for external parameter, which is for the Brownian particle, right? For a given value of x, the average force is then the average forces will be then if I equilibrium x is equal to average over the space, so average over the space Fy of this microscopic variable x, and this distribution will become the equilibrium distribution. This distribution will be then equilibrium distributions, which is psi equilibrium of, so we are sort of, you know, removing the time dependency of these distributions, because at equilibrium there is no sense of time, as if time halts there. So let's say this is equation number 13. Okay, so now let's, so what we did just said that psi eq is the equilibrium distribution function for the fluid molecules. Now this is actually given by the canonical distributions. So right, because at equilibrium we can use the equilibrium statistical mechanics, then you can easily use the canonical distribution. So this can be, so this is given by canonical distribution. Okay, so then what will that be? That psi equilibrium of x is equal to, we know this will be the e to the power minus beta h of x, and divided by d omega of e to the power minus beta h of this x. Okay, and this is equation number 14. Okay, now this free energy can be taken as from this, can we, no, now it is, it is quite easy, it is quite easy to show that this average equilibrium force is given by the partial derivative of the free energy, of the free energy. This can be easily, shown. How? Because A of x, let's say this is a free energy, which can be written as minus kBt log of e to the power minus beta h of x. Sorry, this is 15 where as this force, generalized force, this is statistical mechanics. Equilibrium statistical mechanics is equal to minus delta x del x I. Let's say an example of this is like a buoyancy force acting on the particle when the particle is dipped in some fluid. Okay, then that can be taken as this kind of functions. Okay, so okay, now let's now consider consider that at time t is equal to 0, let's say starting time, the system was at equilibrium. So let's say there is a time for which it is at equilibrium for given values of the parameters external parameters x of 0 and that x of t changes slowly changes slowly with velocity xi t for t greater than 0. Okay, so let's say the external parameter value at t equal to 0 is x0, and now as time evolves it changes slowly with velocity x dot t. Now what we'll do is this: what will be the average force? So the average force average force x plus delta x acting on the particle at time t can be calculated by solving the time evolution equation for the distribution function which is psi of lambda xt. Okay, so which is like the Liouville equation in statistical mechanics. So basically boils down to Liouville's equation in statistical mechanics. Okay. So the average force acting on the particle time is calculating is the time evolution of the equation of distribution functions, because as the distribution function changes, that is due to this average force acting on the particle. That is for sure, right? That is the main factor here. So now you can write that deviation deviation delta xi t is equal to xi t minus xi 0 is, if the deviation is small, we can write the following thing. What is this f I t, which is x plus delta x is equal to minus delta a of x dx dx I minus 0 to t dt prime of j alpha I j x t minus t prime xj dot t prime. So this is like the same thing. Okay. Just we are just using the derivations, like deviations thing. Okay. Since it just you know, increased by this amount, now this term is the equilibrium thing. So first term on the right hand side represents the equilibrium force F of equilibrium when xi, like the external variable, is fixed at xi 0, and the second term represents the first order the second term represents the first order correction, first order correction due to the time dependence, due to the time dependence to the time dependence of xit. Okay, so then since it is time dependent, so that will be the next term, huh? Now it can be proven, also it can be proven, it can be proven that function alpha ij xt is related to the time correlation, time correlation function of random force or fluctuating force or fluctuating force, which was the microscopic force f rit, sorry, at the equilibrium state initial equilibrium state where this equilibrium initial state where x of t is fixed, x of t is fixed at the initial value of x0. That means if you can write like this, alpha ij xt is 1 by kbt, then f of rit times f of rj0, and this is evaluated as equilibrium for the given parameter. So this is equation 18. Okay, and also what is this fri random force? That random force from these things. So this is random force at the initial equilibrium states. So this term we can write that f of rit is actually the microscopic this force minus how it deviates from equilibrium. So this is this. Then can we easily write as if, remember we know what is at equilibrium, that we can do from thermodynamics. So if our equilibrium was this, was if equilibrium was this one, so using this minus will be plus, so this will be delta A of x delta x I. So x is a composite thing. This includes all these, generalized coordinates x I, x1, x2, x3, x4, and so on and so forth. Okay. Okay, here lambda t is the microscopic state variable, microscopic state, because there is two state, microscopic and macroscopic state, right? So what these are the microscopic state variable at time t. So all these equations let termed as equation number 19. Okay. Now you can see this is now is changing with time, because this guy changes with time, right? So now suppose, now this is like this equation, this equation is a generalized form of the random, when we calculated the time autocorrelation functions, this is a generalized form. Okay. So now let's say suppose suppose a particle, suppose a particle placed in a viscous fluid starts to move starts to move with constant constant velocity, v at t is equal to 0. Okay. Then according to equation number 17, you can write, according to equation 17, the average force acting on the particle, acting average force acting on the particle is given by is given by f of t x plus delta x is minus of 0 to t dt prime alpha x t minus t prime v is equal to minus v 0 to t dt prime alpha x t prime. This is equation number 20. Now here you have probably noticed that free energy of the fluid is independent of this x, which is external variable, right? So that means you can easily make this part, this part, this fellow is to be 0, because this is independent of the Brownian particle, this thing. So free energy, comment, free energy, free energy of the fluid is independent, is independent of x, and therefore d of dx is equal to 0, because free energy A is independent of x. Huh. Now, on the other hand, if you see from phenomenological perspective, that friction law, where viscous force F subscript small f acting on the particle is given by minus gamma v, right? So now phenomenologically, now phenomenologically, phenomenologically, friction law, friction law says that viscous force, viscous force capital F small f acting on the particle, acting on the particle is given by minus gamma v, right? Now if you compare these two equations, we can then write, so this is the minus gamma v friction, and if you compare this thing, so like this and this, so now comparing this with equation 20, then we can write minus gamma, which will be variable of x, v is equal to minus v 0 to t dt prime alpha x t prime, and this v cancels out, and you can easily write 0 to t dt prime alpha x t prime is equal to gamma x for t greater than 0. This is equation number 21. Now to make this true, so now to equation 21, for equation 21 to be true, for any time t, alpha t must be written as alpha x t is equal to 2 of gamma x delta t. This is like gamma function of t. So this is equation number 23, sorry 22. So you can get from here, this is the main main idea of this. Okay, so now we have got these two relation. Now we will promptly write. So now from this equation, then alpha ij will be kbt. So then you will write this, substitute to this expression. So then we can safely write alpha ij is this. So 2 gamma of x. So basically you are, so this was a function of x and t. Now you are finding what was those function of x and t. Now this function of x is this guy and function of t is this delta functions. So now this will be 1 by kbt of f of rt f of r0 equilibrium x. Huh. So from here you can easily write that if r t and f r of 0 equilibrium x is equal to 2 gamma of x kbt and delta of t. So this is equation number 23, and this is the generalized sort of time correlation function, and from here you can get this generalized fluctuation dissipation relationship, right? So this is generalized time correlation function, generalized time correlation functions, and from here we get this thing. Now let's think about something. Now if the surrounding fluids, if the surrounding fluid is not viscous, rather viscoelastic, more complex, is a viscoelastic fluid, let's say the viscoelastic fluid, then the frictional force, the frictional force f t behaves as so there that force f of t minus, let's say this v, so this behaves like this. So this reaches the plateau region. Then FFT actually approaches the steady state value with some delay time. Then if FT approaches the steady state steady state value with some delay time then in that case in that case alpha t also has a delay time. Then alpha t will also have some delay time. So from here also we can see, and also we can see from equation 23, from equation 23, fluctuating fluctuating force acting on a particle has a finite correlation time. Okay, so basically that is that. Now now we will define the generalized Einstein relation. The generalized Einstein relation. Einstein. Okay, so now let's discuss a special case of the fluctuation distribution relationship, and this gives a generalization of the Einstein relationship. Okay, and from there we will get the time correlation function of fluctuations to the system response to external fields. So here let's discuss two things. Let's take a special case of the fluctuation dissipation relation. Okay, and also from that special case, what we'll get, it gives a generalized generalized version of Einstein relation and relates and relates the time correlation time correlation function of fluctuations of fluctuations to the system response to external fields. Now, to derive such relations, we will look into the Brownian particles of the system. So now, to derive such systems, we now consider a Brownian particle as a part of the system. Okay. Therefore, therefore, omega now represents represents the position the positions and momenta of fluid molecules and Brownian particles. And also any external field is applied to the system any external field applied to the system at t greater than 0. So after t greater than 0, t equal to 0, the external fields are applied, and the Hamiltonians of the system, then the Hamiltonian of the system for t greater than 0 is then given by h, which is a function of these variables, and small h is equal to h naught, which is at this, and we expand it along this. Okay, h of I at the time t and m of I at, sorry, at this, and this is equation number 24. This is equation number 24. Okay, okay. So now external parameters, we have changed some notations. Let me just clarify those things. Here external parameters are now denoted by HIT, and the corresponding and the corresponding conjugate quantities are denoted by MIT, sorry, like this, and this MI of this is minus del H by del Hi. So this is similar to the previous things that we have done, except here we are using a different, notations for the external variable. Okay. Okay. So now usually what these things represent is, usually HIT, it represents some external force, external force, and M of I, this represents the quantity conjugate to HI. Okay. Okay. So basically, what are the conjugate variables? If let's say two variables, if their dimensions, product of their dimensions, if that has a dimension of energy like ml square to the power minus 2, those two variables can be considered loosely, can be considered as conjugate variables. Okay. So for an example, you can see, let's say an external force, let's say an external force if, let's say, E is applied to a particle, let's say to a particle, so the potential energy, then the energy potential energy of the particle will include a term minus x of E, where x is the coordinate is the coordinate is the coordinate is the coordinate of the particle. So, and in this case Hi and Mi correspond to correspond to f of E and x. For a for another system, let's say a magnetic field which is applied to a magnetic particle which have a magnetic moment mu m, then for that case we'll get to have that magnetic field will create a potential energy minus mu m h cos theta, where theta is the directions between the magnetic field and this magnetic moment. In that case, H will be capital H, the magnetic field will be Hi, and the mu m cos theta will be that thing. So basically you can check what will be those conjugate variables. Okay, so now in previous case we considered some situations where the system was at an equilibrium at t equal to 0 with 0 external fields, right? So, and the step fields HRI applied for the just small positive times. So now in our discussion, in our discussion we considered we considered considered the situation that the system the system was at equilibrium at t is equal to 0 with 0 external fields and that step fields step fields Hi, are applied for t equal to epsilon, where epsilon is a small positive time, then you can write HIT is equal to HI theta t minus epsilon, or HIT dot. So you know that theta function's derivative is the delta function. So now you can get that HIT dot is HI delta t minus epsilon. So that will give you equation 26. So now let's say define the response function. Let's say define the response function. Define the response function x ij of t for this situation of this situations. Let's say this is so this will be m of I, let's say t minus mi 0 at h is equal to j chi ij t hj. So this is equation 27. Okay. Now this we can be proven this response functions xij is related to the correlation functions of the displacement in certain way. So it can be proven that the the response function which is xij of t is related to the correlation time, to the correlation function of the displacement. Okay. Okay. So now you can write here that xij of t is equal to 1 by 2 kbt average of of these functions mi t minus mi 0 times mj t minus mj 0, that will be equilibrium 0. So this is 28. Now these two equations 27 and 28 gives a generalization of the Einstein relations, right? Now so equation 27 and 28 give a generalization of the Einstein relation. Suppose, let's say, a constant force is acting on a Brownian particle which is in a solution at time t equal to 0, right? Then the particle starts to move with constant speed. V is equal to that applied force divided by gamma. Therefore, the average displacement the average displacement of the particle is given by this Fe or times T by E, which can be given by this. And therefore, you can get this indications. Okay. So what we are trying to say is, let's say, suppose suppose a constant force, a constant external force, if E, this E means external, constant external force is applied applied to a Brownian particle at time t is equal to 0, then the particle starts to move with starts to move with constant speed constant speed v, which is f of E by gamma, right? So therefore you can write, therefore the average displacement, the average, so if it is the constant speed, so please, see this point. This is very much important. uh, this point is very much important, because when we will describe the active Brownian particle, there it will be, somehow useful. Okay. So there the average displacement of the particle will be x of t minus x of 0, given that this is constant, right? This is the external things. So that will be, this is the speed. So this speed, constant speed Fe by gamma times t, right? And if that is the case, then this will be the chi t. So and chi t will be then chi of t, then will be t by gamma. Therefore we can write this thing as Therefore equation 28, then equation 28 can be written as so we know the chi t, which is t by gamma. So let this will be t by gamma is equal to 1 by 2 kbt, 1 by 2 kbt x of t minus x of 0 whole squared, which is at equilibrium with 0 things, right? Now this average of the right hand side of this equation then can be written in terms of the diffusion equation, right? Because you know from here, we know from previous understanding, so let's say this is equation 29. We know previously that we know previously that this thing x of t minus x of 0 whole square equilibrium 0 is 2 dt, right? Now if you just compare this thing like this relation equation 329 and 30, now comparing equation 29 and 30, we will get 2 dt is equal to 2 kbt t by gamma. So this will be 2 kbt by gamma into t. Okay, so from here you can easily write that d becomes kbt by gamma. So there you will get back the Einstein relations, right? Now this all discussions becomes for the viscous relation, viscous media. Let's say the particle, now the particle is moving, particle is moving in a polymer solution, particle is moving in a polymer solution. So the response function, response function, response functions will be, as we discussed, will be, so polymer solution means this will be visco-elastic. So the response functions will be like this, like this. No, like this. The response functions will be like this. So there will be some delay times, right? So response functions will be like this. So the particle moves quickly and then it slows down. So the particle first moves quickly and then slows down. And according to the mean square displacement of the particle will behave, and mean square displacement will behave. Okay, so if you think like this, then so let's compare these things. Let's say this is viscous and this is viscoelastic. So basically in viscous, let's say it's like very small molecules is there. Now let's say there is a particle. Okay, so now it's moving with the help of some external force. Now same thing in viscoelastic media, there will be much more like polymers, like this. Okay, so due to this, the displacement and mean displacement that will affect it, right? So if it is viscous and if it's some constant force is being applied, then there will be a constant velocity. If there is constant velocity, then this term x of t minus x naught and its mean at f of e. So what will it will be in this case, this will grows linearly, so t in this direction. On the other hand, if you have the viscoelastic thing media, then t grows like this, and this displacement xt minus x naught f of e. So there, so at lower time it will be somewhat stiffer, it will be sometime steeper, and then it grows like this. Okay, so this will be no more like this. Now due to this viscoelasticity present in the media, the you know the macroscopic particle or this bionion particle is responding differently. There is some transient effect, in this region, like it is changing its behavior. So like you can see the same thing in this case also. So here also show the frictional force. So let's say this is f of t here this frictional force for the viscous thing, it like very fast reaches, like it follows, reaches its value, the steady state value reaches steady state value faster. But here it is taking some time, so there is some some delay, right? Some delay in responding to the this thing. It shows the friction force shows transient behavior, transient behavior due to visco-elasticity. Okay, now if you talk about the time correlation functions, there will be also some effect of this. So the time correlations function for the viscous thing you earlier seen, it will falls off very rapidly, right? So it will now for viscoelastic case, this does not falls off that rapidly, but it falls exponentially. So it has some finite time, like some characteristics times to fall. Okay, so these sorts of uh, you know concludes our discussions about this, mainly Brownian particle systems and the generalized part of it. So it is important because you will see that most of the times, like in recent times, active Brownian particle, Brown dumbbell particle, which are sort of active systems, like which shows more, some more propulsion compared to the Brownian particles, because it has some, you know self propulsive, velocity, self propulsion speed, that propels themselves much more compared to the Brownian particles. So to study them, you need to know, or you need to have the basic understanding of the Brownian particles. And in last 10-15 years, these active matter systems, or these active Brownian particle systems, they consist of a huge, like huge number of papers are being published, or reported in each journal regularly. So this is a point of interest in recent times, because it is curious to know that how, if you add some extra propulsion into this kind of system, or some extra activity into the system, how the system will behave differently from a normal Brownian particle system, which we call as passive system. Why passive? Because there is no extra activity like that can be harnessed, that the system is harnessing from its surrounding, right? Let's say one active Brownian particle or the self-propulsive particle that actually it extracts energy from its environment and does some dissipative work so that it can propel in that media. Okay, so and basically in our daily life we see this kind of active systems every time, be it your in your cellular organisms, be it bacteria and different kind of, if you want to do different kind of things, an active Brownian particle has some extra advantage because there has some transient effect. We will discuss when we will be studying those things. Okay, so basically what we have done here last thing, so we wanted to calculate this time correlations functions, and we s- see we wrote this macroscopic force Fi equilibrium x to get to from we wanted to get it from its averaging, and to average it we are getting it from its macroscopic curved microscopic part, which is like taking the average of this microscopic quantity Fi hat, like microscopic force. And we also know this distribution of this thing follows Boltzmann distributions, and from this here, and we calculated this free energy, and we also know this we can calculate the free, from free energy we can get this force, that is what we have written here. And this average force which is acting on the particle at a time t, that can be calculated by solving time evolution equation for the distribution function. So if you know the distribution functions you can get this average force, because that is what is telling you that what is happening. Now if you think about the deviation, which is taking the deviation from xit, like from its initial conditions, then you can write this average force like this. So at the first term on the right hand side of this expression, which is denoted by the curly, this thing black curly line, so that is the equilibrium force when xi is fixed at the xi is equal to 0, and the second curly bracket region is represent the first order corrections due to the time dependence of the xit. Okay, just a minute, maybe there is, so that is, so basically that is what we are doing here, so if you think, so what I was trying to say here, that you are sort of writing this from this random force, and from there you are getting these functions which we will call later response functions from this which is defined as this time correlation function of this random force, and after doing calculations you will get this. And for a certain Brownian particle we get this average of this is minus v of this thing. And for the free energy for a fluid which is independent of x, which is the property of at equilibrium, that phenomenologically you can say that if F is acting on the particle will be this minus gamma v. And after comparing this we go get this gamma x relations, and if you put that into this response function, then we will get this 2 gamma x delta t of this and comparing this we will get the generalized time correlation function. Since the fluctuation distribution functions is f r t, like the time correlations of the this random force is 2 comma x kbt delta t. uh, so that is what we have done, and after that we get these relations, and later we calculated these generalized Einstein relations, and for that we calculated the special case of fluctuation distribution relations, and we actually uh, assume that an external field is applied to the systems at positive time, let's say t greater than 0. So then we can say this Hamiltonian is like this, where we are expanding like this, and these relations where mi lambda is like minus del h by this, uh, and del h by del hi, and after doing different calculations we get uh, this relations, and where is like mi and hi is the conjugate canonical conjugate variables, and we calculated then this, and we get again this relation, and we also try to compare those two medium, viscous and viscoelastic, and how they are different. So the average displacement for viscous, it grows linearly, right? But so average displacement, given it's like there is some external force that grows linearly, but where in the viscoelastic regime there is some transient effect. Similarly, here if you use this the friction force, the frictional force, it reaches steady state value faster for viscous medium, but for viscoelastic medium the viscous force reaches steady state value after a certain time. There it shows some delay behavior or some transient behavior, right? The autocorrelation functions for the viscous media, it falls off very rapidly, but for the viscoelastic media it falls exponentially. Okay, so that is the main discussion of us. So now in the next classes we will discuss more about, like we'll start like last frontier, which is like how we can see all these things from a probability density function. So from up until now we discussed everything using like variables of like calculating mean square displacement, all these things. Now we will try to get to know that where, how, if we, if in some way, if in some way we get to have the probability distribution functions of that system, of that variable, then we can get all the information from there. So there I will do that, and that will be the final sections of our discussions. Okay, so I will stop here and we'll meet you in the next class.